the way, I will say now that it's 10:50, all the lectures that we do, so even this one, will be recorded. So if something absolutely goes haywire and your internet kicks you off, or your computer, loses battery or something crazy, and you lose connection to the lecture, they will be recorded and they will be posted. I'll probably post them to Blackboard. I haven't decided the best streaming. I might get some advice on that. What would be easiest for you guys to stream from? But they will be available. Okay. So if you joined and you read my attendance policy, which we'll go over in a second, know that I'm not going to be, malicious about that. These will be recorded and made available for you. I still want you guys to join live because I think that's going to be the best way, one, for us all to be self-disciplined, because let me tell you, virtual stuff is going to require way more self-discipline. And then anyways, but they will be made available. So just know that if something crazy happens, all the lectures are recorded. So I'm going to start off with a few announcements. First off, welcome. I'm excited to do semester with you guys. I'm excited to get to know y'all as best I can. That will hopefully be through the few labs that we have in person, and then individual Zooms and things like that you set up throughout the semester. My name is Dr. Eberly, and we're gonna have a good time this semester. We're gonna make the most of it. So a few announcements. The first one, I do want to remind you of the attendance policy, which is in the syllabus. And here in a minute, I'm going to share my screen and connect to an iPad that I have, and we can look at a few things. That's how we'll do the lecture. You'll see a small picture of me, but you'll be looking at what I'm looking at. So attendance policy is this: you get 3 excused absences from our live virtual Zooms. So if something happens, if you're sick or whatever, you get 3. You don't have to email me. You don't have to tell me. You get 3 excused. But starting with the 4th absence, I will start taking off points from your overall grade, just because your attendance really is critical. And so I just wanted to incentivize attending these virtual lectures. Okay. Now, if something happens, you've had 3 absences and something crazy happens, you're in a car wreck or whatever, you can email me and let me know. And I will totally work with you guys. We're going to all have to show a little grace and flexibility this semester with all the stuff going on. So just let me know. If you'll just communicate with me, I am happy to work with your situation or whatever. Now, if it's oops, I overslept again, I don't consider that an excused absence, but please just communicate and we can always work out a solution together. So that is the attendance policy. What else? Okay, labs. I sent an email with a video about the flow of the chemistry building, Mannion Hall. So we have certain staircases that you are only allowed to walk up that staircase. And I know this is new for me too. You have certain staircases you're only allowed to walk down. So in the email I sent earlier this week, check out that video, just so that you know how to enter our building and you know how to enter the lab space and sanitize your station and all that. They are hammering and harping, I know you know this, but 6 feet of distance, and you have to wear a mask into lab. I believe that all of you are going to be getting a KN95 mask, a pack of 5 actually, from our department. So please use those masks. Those are very valuable respirators, and they work well and effectively if we use them. So everybody will be required to use those in lab. Don't throw them under your bed when you get back in your dorm room or your apartment. Please take care of them and wash them. Those will be for lab. You will get those from us. And then goggles. If you don't have goggles yet, I sent an email about this too, but our department was going to sell a bunch of them, and there was a huge shipping delay. So I urge you to buy them elsewhere. They said they had like 150 pairs. So yeah, right. If you haven't gotten them probably by today, you're probably not going to get them from the department. So you can order them online. You can check with the bookstore. The syllabus, the required materials list says what kind you need. So just double check that. Make sure you have goggles. If you're in the Monday lab, you need those by Monday. Lastly, before we start lecture, access code. I've been getting a lot of emails about the bookstore doesn't have the access code yet. And yes, they're delayed on those. But if you need access, or you want to go ahead and get access code, you don't want to wait on the bookstore, you can just go ahead and follow the PDF that tells you how to enroll in our mastering course. And you can apply for or you can, when it prompts you, join or access via the temporary 14-day access. And then you can pay at any point through there. It'll give you permanent access. It may give you a code. I don't know how they do it from there, but there are ways around just waiting on the bookstore is what I'm trying to say. But if you don't have it today, that's okay. We don't have anything due until like next Wednesday night at midnight anyways. So all assignments will be due online. So you will, if you're in lab well, you all have lab next week. Next week, we have our first of 2 face-to-face labs. So you'll come into lab, you'll complete the experiment, and then you will enter all your answers and your data in an assignment on Blackboard online, okay? Because everything's gonna be turned in online. So I know you're gonna maybe write things down twice or write things down in lab and then go back and enter it, and that seems like you're doing it twice, but that's how we have to do it. And then all of our exams will be online through Blackboard, okay? And all of this info is in the syllabus, so if you have not combed over the syllabus, that is what that's your homework for the weekend, okay? Please look over that, and it should answer any questions you have, and then please feel free to reach out if you need to as well. Okay, that's all of our announcements. We will go ahead and get started. So I'm going to share my screen. Give me just one moment. And we are going to jump into lecture. So share screen. Okay. Okay, so you guys should be able to see my screen, and I want to still make sure I can see the chat because I cannot see the chat right now. I don't know if that is because we are screen sharing. So here's what I'll tell you. I don't see our chat. So if you have a question, then I'm going to encourage you to unmute yourself and ask me, okay? That's not how I want to do it. Do it like this. Okay, so this should look similar to the first slide you have for the Matter in Chemistry lecture we're going to do. And you guys are going to be future health professionals. So as best I can throughout the semester, I am going to relate our course material to health sciences, to being a nurse, to being in sports medicine as best I can. There may be times that you find yourself really deep in some chemistry, and let's be honest, chemistry does not have the best reputation. And here's what I'll harp on. Please reach out to me. Please know that I'm more than happy to have a Zoom meeting with you. I'm really, really bummed about the fact that we can't have office hours in person or the study sessions that I used to do. But the number one complaint, if you've read any reviews on me, the number one complaint about my course is that we move too fast. So I'm telling you that disclaimer ahead of time. Everybody says we move too fast. We move too fast. I wish we could have had more time. And I do too, frankly. But I have a certain amount of things that I am mandated to cover in this course. And so we have to stay on pace. But if you feel we're moving too fast or there's things you're not grasping, do not wait for the exam or the night before, the day before, the week of, to reach out to me. Please reach out. I'm so for you guys. I want everyone to just knock this course out of the park, okay? So please reach out to me because I don't know you're struggling, especially in a virtual course, unless you tell me, and that's okay. I expect that everyone will struggle at some point, all right? So there's my disclaimer. But let's get started. Here is a fun little quote, because let's be honest, we all have those courses in college, I know I had them, that we just they weren't our favorite, okay? So this may not be your favorite course, I understand that, but I do think we can learn things from this course beyond just chemistry. That's what I hope. I hope that for myself, and I hope that for you guys. It's going to be a learning experience for me too. So I love this quote because it always gets me excited for whatever I'm getting into. It says, "It has been my experience that you can nearly always enjoy things if you make up your mind firmly that you will." So I'm going to do that myself. I'm going to have a good time with you guys. I want y'all to have a good time with me. And let's try to enjoy this course together. And you'll find out, here's what I like to do with every lecture. I know I sent a little intro video. Here's a few things about me, but I realized I forgot one of the things that me and my husband, our family love to do is we love to go hiking. So if you're not from Arkansas, these will be things that may be brand new to you. If you are from Arkansas, a lot of people I find still don't get out and do any hiking. This is an incredible state to do hiking in. So I have listed here this trail. It's called Hawksbill Crag. It's up near the Buffalo River in an area called Ponca, and it's got this huge kind of rock piece that juts out into the nothingness. But obviously there's no rails, so be careful. But it is one of the most iconic hikes in the state of Arkansas. So I encourage you this fall, as the temperature cools off and the trees change colors, get out and do some hiking. One, everybody needs to get out in this COVID season. And so hiking is a great way to do that. It's not a very strenuous trail. It's really awesome. It's probably about an hour and a half drive from Conway. So it might take up a whole afternoon or most of the day to go, but it is really enjoyable if you want to go with friends. Always feel free to email me and ask about hikes. We're going to talk about a lot of different hikes over the semester. So next picture, this is actually getting into lecture, but it is another hike. This is a hike we obviously is the Grand Canyon. So for our 1-year anniversary, we went to the Grand Canyon, and this trail is called Plateau Point. I'll kind of mark out the trail. It winds all the way down into this valley, and then it plateaus right here. And right here, that is Plateau Point. And what's cool about Plateau Point is you're halfway down the canyon. So you're halfway in and you're halfway out. And you can see the river from that point, but then you have to turn around. It's just a down and back. So you have to turn around and hike back out of the canyon. But it was an incredible hike. One of my favorites that we did while we were at the Grand Canyon. Anybody been to the Grand Canyon? You'd have to unmute yourself to tell me, because I don't see the chat. I'm gonna have to fix this so I can see the chat. I'm gonna have to ask how to fix that. Okay, well, if you've been to the Grand Canyon, we have something in common. But looking at this picture, obviously, we're gonna start talking about chemistry now. Obviously, you see a lot of things. You see a lot of what we're gonna call matter, okay? So we see the sky, we see clouds, we see different layers of earth, we see trees and leaves. All those things are what we call matter. So that's going to lead us to our very first question in this course. What is matter? So matter is anything, well, first off, the general unchemistry version, unchemistry definition is matter is stuff, okay? It's just stuff, any kind of stuff. All stuff is matter. Okay, so what you call stuff, scientists, chemists call matter. But if we're going to get more specific and actually define it, matter is anything that has two properties, okay? And those two properties are size and volume. Actually, I think I use the word mass and volume. Yeah. Instead of size, we're going to write mass. Okay. They're similar, but I don't want us to get confused. So mass and volume. And can you guys see the writing in pink? I can change it to black if I need to. Is the pink okay, though? Sometimes I find that the pink sticks out a little more.
Yes.
Okay, good deal. Thanks. So anything that has mass and volume. So if you look at the pictures that I've posted, the first one, I'm going to turn my screen sideways. This may help us. There we go. It's a little bigger. The first picture in the middle is a cheeseburger, right? This is matter. For some of us, it's our favorite kind of matter. Man, I wish I could see the chat, because I always like to know who thinks what place in Conway has the best cheeseburger, or Arkansas for that matter. If I'm going to get a cheeseburger, I like to go to a place called Big Orange. Anybody been to Big Orange? It's really good. But a cheeseburger would be matter, okay? But matter, because it has all different kinds of mass and volume, if we think about the scale, you have matter that's incredibly small and you have matter that's incredibly large. So let's think about the smallest kind of matter that exists. And anybody, you can feel free to unmute yourself. What do you think is the smallest kind of matter that scientists know of on planet Earth? Any guesses?
An atom.
An atom is a really good guess, okay? You're headed in the total right direction, but we can actually get small.
Electrons?
An electron is even closer of a guess. So atoms are made up of electrons and other what we call subatomic particles, and we're going to get into all that. But electron is probably the best guess that you guys could think of. So supposedly, we've actually never measured the mass and the volume of this, but they have a subatomic particle even smaller than an electron called a quark. Okay, Now, if you go Google the word quark, Quark, it's going to show you a type of European cheese. Okay, so that's why I put that picture there. But a quark is a subatomic particle. Again, it's ironic they think this is the smallest because we've never actually measured the mass and volume. They move it too high a rate of speed. So that's the smallest we can get. Okay, so I just want to point out matter can be really, really small. Okay, on the other side, it can be really, really large. And if we were in lecture face-to-face, this picture would not be showing yet, but obviously I've shown you the largest matter, single unit of matter that we know of is a star in outer space called Canis Majoris. Okay, this is the largest star that we know of. In fact, it shows you how small our sun is compared to that. You have to zoom in to even see what a speck that is the sun compared to Canis Majoris. So that's kind of mind-blowing. It's really hard for me to wrap my mind around how big matter can be and how small matter can be, because I deal with matter in the size of cheeseburgers a lot, right? But I just want to point that out. Don't box in this thing called matter. There's not one kind of matter. There's all different kinds, all different sizes, and it's a very vast thing. And because it's so vast and there's so many different kinds, we have to have tools to categorize and simplify and group things in different kinds of matters together. So that's what we're going to get into, is understanding the science of chemistry, and even in health sciences, how we do that. Okay, so chemistry is the study of matter. Okay, that's how we would define the word chemistry. And the way we begin to study matter, the way we begin to look at it is, you know, if I have a piece of matter, I might touch it and feel it and say, what is it? I might shake it. I might, you know, there's several different ways you can begin to look at the properties of that matter. So some examples, different properties of matter, is that matter has size. Okay, it's got a size. So we can measure the size in different ways. You can measure the volume. Okay, for example, you could measure the length of something. You can measure the mass as well. So when we just say the size of something, we could be talking about its mass or its weight. We could be talking about the length of it. We could be talking about the volume of it. Matter also has, it has temperature. Okay, we can measure how hot or how cold it is. If it's at room temperature, if it's in a freezer, if it's really hot. And then matter also has color, is just another example, okay? So matter has color as well. There's all different colors that we know of. So these are just some examples. Could anybody else think of a different property that we could measure on a piece of matter? Any guesses? It's okay. You just want to guess? I'll give you guys one: density. I bet you've heard that word before. Maybe you've said to your little sister or your friend one time, you're just so dense. Okay, everybody and everything has a density. What else? We could measure the reactivity. This is a fancy word. How reactive something is. We're actually going to look at some cool videos in future lectures about how reactive certain elements are. And these are all properties that matter contains. And there's more than this. This is just some examples. But not only do we just touch it and look at it and measure it, we also look at the way matter changes. And in fact, that gives us more information, because matter is changing all the time. Our universe and our world is not static. It's very dynamic. Our bodies are not static. They're very dynamic. In health science, a lot of the things that you measure and look at or take note of are the way things change. So it's more valuable that we understand how to measure chemical changes and non-chemical changes. So there's two kinds of changes. The first one is a physical change, and then obviously we can have a chemical change. And one of the main takeaways from today, if you learn anything, I want you to learn the difference between a physical and a chemical change. Okay, that these concepts will definitely be on exam 1, knowing how to identify if a change is physical or chemical. Okay, so a physical change does not alter chemical makeup. we'll look at examples of that to clarify what that means. But if I start out with one type of matter and it undergoes a physical change, I still have that same kind of matter at the end, okay? But a chemical change does alter chemical makeup. So if I have a type of matter and it undergoes a chemical change, I don't have the same thing at the end. And we're gonna look at examples of that. And that's also why I put these pictures on here, because these help demonstrate and give us a visual. Some of you, I'm a more visual person. I like to have pictures and videos. They demonstrate chemical and physical changes. So if we look at this first picture right here, we see a beaker. We see different colors, but what's the thing that stands out to you in this first photo?
The fire.
Yeah, there's a flame here. So if I were to light something on fire, am I going to have the same thing afterwards that I had before? No. So would you think this first picture represents a physical or chemical change?
Chemical.
Definitely. Okay, definitely a chemical change. Anything that is lit on fire is undergoing a chemical change. All right. Next beaker here in this next picture, what do you see? I see a beaker that, what would you call what's happening in this picture? What words would you use to describe it? Some people say smoke. Anybody have a guess?
Maybe
Say that again.
a liquid turning into, I said maybe like a liquid turning into a gas.
Yes, yes, okay. So we have actual names for that process. But would you say that the substance in the liquid form is different than the substance in the gas form?
No.
Something to think about. And if not, and you're right, it's not, this is a physical change. Okay, we might call this process evaporation. All right. So when something is just changing from like a liquid to a gas, for an example, that's a physical change, not a chemical change. All right, the next picture shows this yellow powder. And it's honestly not a great photo. It's because it's kind of a static photo. You can't see something happening. But if you had a solution and you were to form a yellow powder and you had a clear liquid, or this powder was white and then it turned yellow, this signifies us when we see color form or color change that we are getting a chemical change, okay? Really bright colors. Chemistry often forms things that, or it makes colors disappear. It's magic, right? Then lastly, if we had a piece of metal and we ground that metal down into shavings, which is what you see in this pile, what kind of process would you call that, chemical or physical?
Physical. Physical.
So these may seem very simple, but sometimes the lines can be blurred, okay? But I just want you to remember the actual differences are pretty simple, okay? So we're gonna apply these to different topics. And in fact, we'll go over this, and then I had a poll. I'm gonna try this out. I've never used a poll on a Zoom meeting before, but I made a few for this lecture. So hopefully they'll work out. We're gonna try that in just a minute. So another way things changes, and we mentioned this with beaker number 2 right here, things changing from like a liquid to a gas. That is an example of how the properties of different matter changes state, okay? Another way to say this is another type of property of matter is whatever state it's in, okay? So not only can a property be a color or a length or a temperature, it can be a state of matter. That's another property. So solid, liquid, gas. These are our 3 states of matter. And I know somebody's probably thinking, what about plasma? That is a 4th state of matter, but that's beyond the realm of this course, okay? We're mostly gonna focus on solid, liquid, and gas. But I just wanna look at the 3 examples that we have here. The easiest substance or type of matter to track this with is water. So we have 3 beakers with water in each beaker in a different state of matter. So solid, this should all be very basic to you guys. You guys should be able to grasp this pretty easily, but solid, we call that ice if we're talking about water. And here's what you need to know. It has a definite volume and a definite shape. okay? Any state of matter, when it's in a solid form, it does not depend on the shape of the container that it's in, all right? It has its own shape and it has its own volume. Liquid is different. When we have water that's in a liquid state, it has its own volume, but it does not have its own shape. It will take on the shape of whatever container it's in, okay? So it does have a definite shape, a definite volume, but the shape of it will vary depending on what container you put it in. If you put it in your water bottle, it will have one shape. If you put it in a bowl, it would have a different shape, right? If you threw it on the floor, it would have a different shape. That last one is what my 2-year-old loves to do the most, by the way. Throw it on the floor. Gas, so that's the third state of matter. And here's what we need to know about gas: variable volume and variable shape. A gas is not, it'll take on the shape of whatever container it's in, okay? It'll fill the size of any room that it's in. It can be smushed into a smaller container. It can be compressed in ways that liquids and solids cannot. So that's how gases, liquids, and solids are different. I like to draw pictures as well. So if we're gonna draw a solid, particles in a solid state, let's think about what at the molecule size. So we know a molecule of water has 2 hydrogens and an oxygen. It's H2O, right? So if I draw little molecules of water, and I'm just gonna draw them as circles right now, okay? In solid form, they are right up next to each other. They're interacting with one another, okay? So oftentimes we represent solids like this, where the molecules are stacked really closely and they're not moving, okay? So they're not moving, I should say a lot. They're not moving a lot. They might be vibrating in place. They have energy. They don't have zero energy. Everything has energy. But they're pretty close together. Okay, now we know a liquid might look different. So how would a liquid look? Well, if we have these same molecules, they're going to be a little more spaced out. And they're going to be flowing past one another, okay? So I'm just going to try to represent that with some arrows. You have molecules, they're not as close together. So these are, I should say, they're not moving a lot. These were close together. In a liquid, these are moving more. So they have more energy, higher amounts of energy. And they're further apart. And we're talking about the molecules here, remember. And then if we're looking at what molecules in a gas are doing, why does it not have a definite shape or volume? Well, gas particles, or molecules, I should say, they have the highest amounts of energy and they're the furthest apart. So I'm going to demonstrate highest amounts of energy with kind of a double arrow. They're moving really fast past one another. And they're the furthest apart. So I'm going to draw them further apart than in the water and the solid. All right, so they're moving really fast and they're really far apart. So I'll say they're moving the fastest and they're the furthest apart. All right, but the thing to remember is that in every state, solid, liquid, or gas, we have the same chemical, the same molecule. It's all water, okay? So changes of any kind of matter, from a solid, a liquid, or to a gas, these are all physical changes, okay? So changes from solid to liquid, liquid to gas, and vice versa, these are all physical changes. That's the main point of these slides. Okay, any questions so far? Or I should say, what questions? Surely somebody has a question by now. Okay, remember, feel free to unmute yourself. I know that's kind of unnerving. I've been in large Zoom meetings and I'm like, I ain't talking. But feel free to stop me. Don't be shy. All right, now we're gonna look at these in kind of a different way. So we're still looking at the same kinds of changes, but we're actually gonna differentiate. If we have water still, we're still talking about water. if we want to understand the difference between a physical change with water and a chemical change, because we can change water chemically, that's what these two pictures represent. So anybody have a coffee pot? Maybe, I don't know if you're allowed to have one in your dorm room, but make coffee every morning at my house, and my husband is the one who makes that. And he always goes and fills up the coffee pot, and then here's, well, this is actually not a great example because we're boiling water, and that's not what. Anyways, if you have a coffee, it looks like a coffee pot, and you have water in it, and you add heat, eventually you're going to heat that water up enough to where it's changing from liquid, from liquid to, up here, we have water in the gas phase, all right? And this is, again, I'm repeating myself, but it's representative of what we just talked about. All that's happening here is a change of state. So this is physical, right? Well, it's already, that's written down there. So this is a physical change, all right? And if you look at this chemical reaction down below in black, that's what we're doing here. We're going, this L right here represents liquid. That's what an abbreviation of L mean. In any chemical reaction, anytime something's abbreviated L, it's in a liquid phase. And then we have the abbreviation G over here because now that water is a gas. And this arrow represents the change, okay? So we're just a change of state. So that's a physical change. We have very common names for this stuff. In fact, we already wrote out the one for liquid to gas is evaporation, right? Or you might say boiling. What's another, if we're talking about physical changes and we're looking at this slide up here, what if we go from liquid to solid? What name would you give that physical change? What kind of sign? Do what?
Freezing.
Freezing. Yep. So that's another common name we have. Freezing. Can anybody else think of another common change of state? Another word for another kind of change of state, physical change?
Condensation.
Condensation. What is that one? Condensation, you're going from a gas to a
Liquid.
liquid. And then we also have melting. So anytime you see words like these, if I were to put that on an exam and ask you what kind of change that is, you should be able to tell me that's a physical change, not a chemical change, okay? All right, but if we are gonna change water chemically, let's look at what's going on in this other picture. We have these electrodes. Looks like we have a battery back here. This looks like some kind of battery, and we have these wires coming out connecting to our beaker. We've got water, liquid water in the beaker. And then what else do you see in this picture?
Gas bubbles.
Gas bubbles, thank you. We have gas bubbles. Now, obviously, I've written the word chemical under this picture. This is a chemical change, but how so? Well, if we look at our chemical reaction, why is it not erasing? Interesting. Well, not erasing. So what we're doing now is we're following the chemical reaction to the right side of the slide. So we start out with liquid water, and then after we look up the other side of the arrow, what do we have? We don't have water anymore. H, hopefully if you've had a chemistry class in high school or at some point, you're familiar with H and O, okay? So this is hydrogen and this is oxygen, and that's also what's shown just underneath if you look at the reaction in word form, okay? So we no longer have water, we have hydrogen and oxygen. What do you know about hydrogen and oxygen? What state of matter are these things naturally in?
Gas.
Gas, they're gases. So the reason we see bubbles, it's not just because we're bubbling water, it's because we're taking water, and when you run an electric current, okay, through water, you break it down into its elements. And the reason this is a chemical change, if we go back, I'm gonna scroll up, I don't wanna make you dizzy. A chemical change, it does alter the chemical makeup. So when you no longer have water, when you have some, and this would be for anything, not just water. I know we're talking about water a lot. But that's why it's a chemical change, because no longer do we have water. We have two different things, okay? And you can visually see that. Oops. You can visually see that in this picture. We're making these gas bubbles up here would be hydrogen and oxygen, okay? Hydrogen and oxygen. All right. Another example of a change. Anybody ever dealt with a lighter? I love to light candles. Okay, we grill at my house, so we're constantly using different kinds of lighters. And I prefer the ones that you just pull the trigger and not the ones you strike, because I burn my thumb off every time. But I've got an example here of a chemical and physical change. So here we have a lighter, and I've actually shown in the lighter fluid, I just put these little molecules in. These are the molecules that make up lighter fluid, okay? It's called butane. Just made up of carbon and hydrogen, okay? That's the only things in butane. So the kind of black looking spheres in the middle are the carbons, and then the white looking spheres are the hydrogens. All right, so we've got butane, and what's happening? Why are we calling this a physical change in the picture on the left? Naturally, without you ever striking the lighter, a physical change is always occurring. Now it's slow over time, but if anybody ever left a lighter and then months later or a year later you find it in a drawer in your house and you shake it and it's empty, that's because all the time these butane molecules, they start out liquid and they're evaporating, okay? Because there is an opening right here. And through that opening, it's slow because the opening is not very big, but these molecules are evaporating into a gas phase. So remember, anytime we're just changing state from a liquid to a gas, or a solid to a liquid, or a liquid back to a solid, this is always going to be a physical change. This is just evaporation. But when the picture on the right, we have a chemical change. So let's say you take your thumb and you strike the lighter, okay? What you've done, without even realizing it, is you've caused a chemical reaction. You're taking these butane molecules and you're forcing oxygen, you're reacting it with oxygen in the air, okay? So there's oxygen naturally in the air, that's where our other reactant came from. Because if you look down in the lighter fluid, we don't have any red spheres down in the lighter fluid, but up here we have red spheres, and that's the oxygen molecules. And then if you look, the butane molecules down here, these are just white and black, but up here we have all different kinds of molecules that don't look like butane anymore. They're different. So we can tell we've made two things. This is actually what we call a combustion reaction. It's a very fancy word. But I guarantee, I bet y'all are all familiar with that. You've watched things combust before if you've ever seen fireworks or been a little reckless with a fire. You've seen a combustion reaction. And anybody happen to know the two products that you get? They're the same every time from a combustion reaction. Could anybody guess? It's these products right up here. Somebody was going to say it.
Heat and, never mind, that's okay.
That's a good guess. Well, we do have some heat here, but the two products we form is this one that I'm pointing the arrow to. This is CO2, carbon dioxide. Okay, so that is a molecule of, or an atom of carbon with two atoms of oxygen. And then we also have this one over here that looks different. Well, this is water. I don't know, why am I? Okay, sometimes the pencil stops working for a second. H2O. Not writing my O. Well, I'm trying to write an O and it's not. Let me try. Okay, H2O. There we go. So we created water and carbon dioxide. So you can see the products that we ended up with, the carbon dioxide and the water, they're different from butane. That is why this is a chemical change. We no longer have butane. Now we have two different things. Okay. Any questions on how we distinguish physical and chemical changes? So I have these pictures here. I'm going to turn my screen so that we can visualize them better. There we go. All on one slide. So this is where we're going to do our first poll. Let me slide over to Zoom and see if I can actually run our first polling. Can y'all see these? Okay, launch poll. Okay, can y'all see a poll on your screen?
Yes.
Okay, so I'm going to give you the clock's running, but this is not timed. I'm just going to give, I can see when all of you have voted. So just take a second and figure A. Can y'all still see my screen with the pictures of the molecules?
The poll's like in the middle of my screen, like I can't move it.
Okay, what about now?
You can touch the top of it and it'll move.
Touch the top and it'll move. That's what I'm doing actually.
I'm trying.
Okay, well, if you can't see it, the first question is, does figure A represent a physical or chemical change? And then I asked the same question for figure B and figure C. I'm going to give you all just a minute. We've got about 20 people still to respond. The nice thing about virtual is you can have all your snacks with you, right? Still waiting on about 10 people. Take your time. Look at the picture.
I can't see the poll.
Can't see the poll. Do you have your video on? I don't know if you need to have your video on. Did anybody have to do anything special for the poll to show up? I hit launch.
Mine
Well-
just popped up on the screen.
Okay, if you can't see the poll, just here, write them down in your notes, because here's the questions. Surely you can see the slide, right? With the molecule?
Yeah.
Okay, just write down A, B, and C. Are they physical or chemical changes? You can just write physical or chemical by each one. Still got about 3 people.
Okay.
All right, so we're gonna look at these. Oh. Okay, so A, everybody, 100% of the people said physical. And you're right, okay? So this one is physical. Why is it physical? Here, you have the same molecule. If you look at it, each molecule has 1 red sphere, and it looks like 4 white and maybe a black or 2. And these molecules on the right side over here, they look the same. So it's the same molecule, they're just more spread out. Okay, so it might be that these are in solid form, and over here they're liquid. Okay, maybe. We don't know for sure, but it's not a chemical change because you have the same substance on both sides. So everybody did good on that one. B, most people, 93%, said chemical. Okay, let's look and see. We have some molecules on the left side. These are our reactants. And then these molecules are all red, 2 red spheres. Do I have any molecules with 2 red spheres on the left side? And the answer is no. I have different kinds of molecules. I have a molecule that is white and red on the product side, which is the right side. I just circled it. But I don't have any molecules like that on the right side. So what we see happening is we have molecules changing form. We have new molecules. And so because of that, this is chemical. So most people got that. And then last one, 90% of people said physical, okay? And that is correct. Why? Because the molecules look the same. All molecules on the left and the right side have 2 white spheres and 1 red. So that means it's the same compound or the same molecule. So all it's doing is they're close together on the reactant side. They're more spread out on the product side. So that's a physical change, okay? All right, any questions there? I'm gonna end that poll. Good job. We'll do another poll in just a little bit. So, oh wait, I think I did have one more poll regarding this. Polling, let's see. I don't want to relaunch poll 1. I don't want to edit poll 1. All I want to do is launch poll 2. Sorry guys, I've never done this before. I'm trying to figure it out. More. Oh, that's how I see the chat. There was one chat. Well, I found out how to find the chat. Let me see if I can find my second poll real quick. I wanted to ask this one. Polling. Stop. Don't end meeting. How do I go? Maybe I hit share results and then, okay, stop sharing. How do I, okay. Oh, I see. Poll 2. Here it is. All right. Do you see the second poll now?
No.
Okay. Launch. Oh, I gotta hit launch poll. Okay. Now do you see the second poll?
Yes.
All right. So it says, which of the following represents a physical change? So this is kind of a multiple choice here. Only one of these is a physical change. First option, roasting a marshmallow. Second option, stirring sugar into a gallon of hot tea. If you're from Arkansas or Texas, you should be familiar with that. Third one says an iron tool left outside gets rusted or rusted. And then last one, expired milk turning sour. Okay, we're about halfway there. Take your time, think about it. About 10 more people. All right, most everybody, 29 of 32, 30, 31. Okay, I think that's about everybody. So let's see, end poll. And let's share the results. So can y'all see the results now? All right, so the correct answer is stirring sugar into a gallon of hot tea. But what's interesting is we got some different answers here. Some people thought roasting a marshmallow. Some people picked all the other ones. So let's think about, why is stirring sugar into a gallon of hot tea physical when the others are not? What about roasting a marshmallow is a chemical change and not physical?
The fire.
Yeah, that word roasting should tip you off that there's heat involved, possibly a fire, and anything that we put over fire. Or when you roast a marshmallow, you see it change colors, right? You see it kind of get black on the outside depending on how far you roast it. Some of you stick it straight in the fire, but that is not me. I like an even, slow roast on all sides. But that is why it's chemical, okay? You see it turn a dark color, and that's a new substance, okay? It's ash actually forming on your marshmallow, okay? Stirring sugar into a gallon of hot tea. Why is this one physical and not chemical? What's happening to the sugar? Let's say we take sugar crystals that you can see, and you put it into the tea. Can you still see the sugar crystals? If the tea's hot? No, what happens? They dissolve. Keyword dissolve. All that's happening when something is dissolving is you're breaking it into smaller pieces, okay? So we're not changing the fact that we have sugar. In fact, you know there's sugar in the tea because it tastes sweet now. So we haven't changed the sugar molecules. All we've done is broke them down into smaller pieces. Maybe we had a large chunk of sugar, and now we have small particles of sugar in our tea. Okay, iron tool getting rusty. Rust is a whole new substance. That's a whole different chemical. So you've created something new there. You didn't have rust before. Now you have rust. I could hold a piece of rust in my hand. So that is a new molecule that we've made. So that is a chemical change. Expired milk turning sour. If I taste milk that's not sour, okay, when I taste milk that is sour, there's something in there that's making it taste sour, right? That is a new chemical. We've created something that has affected the taste. And so because it tastes differently, that is an indication to us that there's something new in our milk that wasn't there before. And remember, anytime you make something new, that is a chemical change, all right? Okay, good. I like this feature of Zoom.
I have a question.
Yes, what's your question?
So, the sour milk question, like explanation, you said that when it's sour, it doesn't taste the same, so it's a chemical
Right.
change. Is
Yeah.
that just another example if this is true or not? Like, let's say you leave your soda out open and it becomes flat, it doesn't taste the same, and the carbon dioxide leaves. Is that a chemical change also?
Great example. I should put this on the exam. That's a great example. So all that's happening, here's a blank slide. We're going to put info on this in a little bit, but all that's happening, here's what I know about a soda. One of my favorite drinks is a club soda. So similar. There's like not sugar and stuff in it that are in a regular soda. But here's what I know about a soda is you have CO2 molecules in that can. Like when it's fresh it's cold out of the fridge or whatever, and you open it and you hear it fizz and pop or whatever. Sometimes even if you have like a glass bottle of Coke, those are for special occasions, right? But when you have like a glass bottle, you can actually see the bubbling. And what's happening is that the CO2 is simply leaving the soda. And if that happens enough, your soda gets flat, okay? So what's happening here, it's not that we're creating something new. It's just that we had a lot of gas particles in the soda, and now we have fewer. We didn't create a new chemical molecule or compound. Does that make sense?
Yes.
Okay, so that would be an example of a physical change. Or actually, I don't even know that would, because you have gas in the liquid and you have gas outside the liquid. In both cases, it's a gas. So, but that is a good idea, a good thought, a good question. Okay, let's pick up with this next slide right here, because we've talked a whole lot about physical changes. But how do we know when a chemical reaction is occurring? Chemistry is sneaky. And sometimes a chemical reaction can occur and you're like, how did I even know that was chemical? In fact, that's what that last poll kind of was checking. So there's 4 signs, which if you can see the next slide we're going to get to, we're going to write out what those 4 signs are. And you will need to know these for the exam. So pay attention here. When we're talking about chemical reactions, I'm going to turn it sideways so this is bigger. Anytime you write a chemical reaction, we're going to spend a whole chapter on how to write out chemical reactions later. But on the left side, so if we look at number 1 here, always on the left side you have your reactants. On the right side you have your products. And in between you have an arrow pointing from left to right. So if we have water as our reactant here, and this is the same reaction that we looked at earlier. We have water as our reactant, and then we ran electric current through it, and we understand at the end of that reaction we have hydrogen and oxygen. This is a chemical change, but how did we know? What about that? There was a picture associated with this, and what did I say? What do you see in the picture? How did we know that that was a chemical change visually? Anybody
2
remember?
new substances appeared.
2 new substances, which were the hydrogen and oxygen, and we saw them appear in the form of
Gas bubbles.
gas bubbles, okay? So that is one telltale sign that a chemical reaction is occurring when you get gas bubbles. Okay, and I don't mean like you dropped a penny in some water and you saw a little bubble float up because the penny splashed the water. I mean like fizzing or bubbling, okay? Now, we just talked about CO2 escaping from soda, and that could be confusing. That is not a chemical reaction because that CO2 was already in the soda to begin with. Here, we created new chemicals, and we know that hydrogen in its natural elemental state is a gas. We know oxygen in its natural elemental state is a gas. So understanding those things, we created gas bubbles. Those gas bubbles, they like to escape water. So that is one telltale sign that you have a chemical change occurring, gas bubbles. Okay, let's look at this next one. This one looks a little more complicated. We have nickel. Okay, we should be familiar with what nickel is. We abbreviate it Ni, so this is the abbreviated form down here, this reaction. And hydrochloric acid. Y'all are probably also familiar with that if you've ever done a lab in a high school chemistry class or whatever. You probably used diluted hydrochloric acid. Well, when we react these 2 together, okay, and we have our arrow, on the product side, we have a new compound, nickel 2 chloride, okay? You don't have to know what that is, but I will tell you this substance is green. Nickel compounds, anything that contains nickel in it, that metal, they like to turn green, all different shades of green. And then we also created hydrogen. That's what happened when we reacted these 2. So if we were looking at this reaction on paper, now knowing that this turns green, what signs here, there's actually 2. What signs here would I be able to see that tells me this is a chemical change?
It changed color.
Okay, so we get a color change. What else?
Molecular change.
Yes, that's happening in all chemical reactions, but what is hydrogen? In its elemental form, we wrote up here that it's a what?
A gas.
A gas. So we're forming a gas here too. So we should see gas bubbles. So this one is repetitive, but we still do see it with this reaction. So far, we've only identified 2 of the 4 changes. So I'm going to come down here. We're going to write those 2 that we know. The first one, we get gas bubbles like a fizzing. Okay, so I'm going to write vigorous. Okay. And then 2, if we get a color change. Something was clear and now it's green. Something was white and now it's blue. Okay, that's signs of a chemical change. So 3 and 4, we actually talked about one of these when we looked at those 4 pictures earlier. The very first one, it had a beaker with a flame. And we said that was a chemical change because of the flame. And what do we know about a flame? It changes the temperature, okay? So anytime you get a temperature change, that is indication that whatever's going on, roasting the marshmallow, we know there was a temperature change involved, that you have a chemical change, okay? Last one, we actually haven't talked about this yet. I'm just going to tell you what it is. We call it formation of a precipitate? Who knows what a precipitate is? That's a fancy chemistry word.
Solid.
Okay, it's in the simplest definition here is that it is a solid. Now, oftentimes this is happening, like if you have a test tube and you have some liquid in it, and you see that liquid and it's clear and it turns cloudy, okay? So it can look like something turning cloudy, okay? But you are forming like a powder or a solid. A precipitate is formation of a solid, okay? But it usually is happening in a solution, okay? That's why we call it a precipitate. So if you did not have a blue cloudy solution and all of a sudden it turns blue and cloudy, you formed a precipitate, okay, when things react. You could put two liquids together and form a precipitate. That's usually what happens. You could put a gas and a liquid together and it forms a precipitate, all right? So these are the 4 signs. You need to know these 4 things for the exam. This will be on the exam, okay? All right, in the time we have left, we only have a few slides left. So I'm gonna grab a drink of water really quick. And we are going to finish up with talking about the periodic table for just a minute and the difference between elements and compounds and how to write those. So grab a snack, grab a drink really quick, and we're going to finish up. All right. So here is a picture of the periodic table. And this stuff should also be a little bit of review. Any like chemistry or science class you had in high school, you at least should have looked at the periodic table. But I'm going to refresh you and remind you, there's 118 elements on the periodic table. Not all of them exist in nature naturally. That sounds redundant, but some of them only exist because scientists have made them. But most of these exist naturally. And I've actually boxed in some in black here that you're probably familiar with. Okay, so carbon, nitrogen, oxygen, hydrogen. You guys, health science people, you got to be real familiar with the ones I'm boxing in over here. Why? Sodium, if you're going to be a nurse, magnesium, potassium, calcium, these are all things the body needs. We call them electrolytes or ions. But these are all elements, okay? This is matter in its simplest form. So I'm actually going to write that out. An element is matter in its simplest form, okay? We cannot break it down any further, okay? It's in its purest, simplest form. Now, when we write elements, we just write them in what we call chemical symbols, okay? So everything you see on the periodic table, all these letters, and I'm just talking about the letters here, V, Cr, Mn, Fe, H for hydrogen, C for carbon. These are chemical symbols. All right, you'll notice most of these are just a single letter. Some of them are double letters. And so I'm actually going to scroll down here because we have rules for writing symbols and formulas. So right now, if we have a single letter symbol, the rule is that it's capitalized. But if we have a 2-letter symbol, the first letter is capital. Second letter is lowercase. So do not write sodium as Na. That is incorrect. Sodium is capital N, lowercase a. All right. That's the rules for writing chemical symbols, which is when we're talking about elements. Compounds are different. How is a compound different than an element? A compound is when 1 or more or 2 or more elements come together. Okay. So a compound is 2 or more elements smushed together. So I've actually shown you several examples over here. Water. Who knows what CH4 is? Methane. Okay, it's a type of fuel. Then we have a complicated one on here. Anybody know what C12H22O11 is? You dietetics people, nursing?
Sugar.
Sugar, sucrose. I always tell this story. I never realized how much sugar my dad used to eat in his, I don't know if he ate it all for breakfast, but every morning when he would leave for work when I was growing up, almost unfailingly, he would grab a Walmart sack and he would put in a Dr. Pepper, an oatmeal cream pie, and a thing of Pop-Tarts. And I'm like, how did this man not have diabetes when he was like 40? I don't know, but he consumed a lot of sucrose. And he's thin as a stick. I don't know, his genetics. Okay, compounds though are when you put two or more elements together, and we represent these by chemical formulas. So not only is a compound different from an element because it has more than one element involved, it also has numbers, because if we have more than one element involved, we have to know how many of each kind of element, how many atoms of that element are in the compound. Okay, so I just said a lot of words. Let's kind of write out what I'm talking about here, down here, with the rules for writing now formulas. So formulas contain letters and numbers. All numbers are written also, I want to point this out. If you look at these up here, you'll notice that the number every time is written down lower and smaller than the letter. And we call that a subscript. All numbers are written as subscripts except the number 1. It's special. When you write the letter for the element, you're indicating that you at least have 1. So if we go back up and look at water, okay, we don't have to put a 1 after oxygen. Okay, that's wrong. Just writing O is enough. We look at methane. We don't have to squeeze in a 1 right here after carbon. Just writing the C for carbon in methane is enough. Okay, so you write all the numbers as subscripts to indicate how many of that element's involved. So this 2 right here tells us how many of the preceding letter. There's 2 hydrogens and 1 oxygen in water, okay? If we look at methane, there's 1 carbon and there's 4 hydrogen atoms, okay? So we indicate those with subscript numbers. For sucrose, 12 carbon atoms, 22 hydrogen atoms, 11 oxygen atoms, all right? I also included this table right here. I'm gonna zoom in on it so you can read it clearly. You do not need to memorize any of this. I just wanted you to show, or just wanted to show you that most of these, in this course, we're going to use modern names, okay? But some of these elements also have Latin names that are still floating around. You might see it on the internet if you're looking up something and you see one of these names in the italicized, just so that you know what it is. It's sometimes different sites. Our textbook uses all modern names, but if you run across something, don't think I lied to you. It's just that there are Latin names that people still use for certain elements, but you don't need to memorize those or know those. I just wanted you to recognize that that's there. Okay, what questions? Any questions on what we've talked about? We're kind of nearing the end here. We have 1 or 2 more slides and then we're done. Any questions on how to write a chemical symbol or formula and what those represent, the difference between an element and a compound? For the exam, I want you to know the difference between an element and a compound. For the exam, I want you to know the difference between a symbol and a formula.
Question.
Yes.
Whenever we're writing the chemical formulas, do we need to write the state of matter next to each one?
Not yet. When we get to like chapter 5 and we're writing out full chemical reactions, we'll start putting in abbreviations. And you may see that I do that some here and there if I'm trying to make a point. But for right now, you don't have to.
Okay, thank you.
Yep, great question. Okay, I'm gonna turn my slide this way. Okay, this is really the last slide for lecture today. Remember we started out this whole lecture talking about matter, okay? And we said matter comes in all different shapes, sizes, forms. This table is just here to help you understand how we classify it. Because there's so many different kinds, it's helpful to scientists and chemists to classify this. So if we have a type of matter and we want to study it, or we want to be able to categorize it correctly, we're going to start asking questions. And the first question we would ask is, okay, what kind of composition? And what do I mean when I say the word composition? What is something composed of? Okay, what is it made of? All right, so we're going to ask the question, is it variable or is it uniform? Does it have a variable composition? Okay, so if we ask that question, we have some matter, does it have a variable composition? And if the answer is no, all right, what that means is we have a pure substance on our hands. Okay, we have a pure substance. And a pure substance, that means it has a uniform composition. So I'm going to write the word uniform. A uniform composition. Now, we can also break down pure substances into the 2 things we just talked about, elements and compounds. So if we ask this question, can we separate it into simpler substances? If the answer is no, that means we have an element, okay? Elements are what you find on the periodic table. And remember, we cannot break those down. That's the simplest form matter can be in. So the picture here is of a Goodyear balloon. What do you know is in a Goodyear balloon?
Air.
Helium, all right? Helium is what makes balloons float. Y'all, I'm trying to blow up some helium balloons for my daughter's second birthday. It's like next Friday. I'm gonna cry. She's gonna be 2. And it is like $2 a balloon, okay? I'm not trying to pay $60 to blow up 30 balloons, but helium's expensive. Okay, that's what I learned about helium this week. You learned that helium is the simplest kind of matter you can have. So a picture here, in this box that you see, we have green spheres. You'll notice all the spheres are green. Some seem like they're a pale green, some seem like they're a dark green. It's just trying to show you different depths. Okay, this is trying to appear like a 3D picture here. But they're all green spheres. It's the same kind of sphere. We don't have more than one in any, it's just one single sphere. So this is all helium. It's an element, it's the simplest it can get. Now, if we ask that question and the answer is yes, we could break it down into simpler substances, then what we have is a compound. The example that we've looked at all throughout lecture today is pure water, okay? Notice in this square, we have a compound, but what do you notice about this box? Would you say that the composition of this box is uniform or not uniform?
Uniform.
It's totally uniform. One, we already wrote that if it's a pure substance, such as water, it's got a uniform composition, but all the molecules here are water. They all look the same. Okay, that's why we say it has a uniform composition. But you notice each molecule of water has more than one element involved. That's why it's a compound, all right? And we could break that down into hydrogen and oxygen like you saw earlier. All right, to finish up, because we have a few minutes left, if it does have a variable composition, yes, it does have a variable composition. What we're dealing with, we call that type of matter a mixture. And there's 2 kinds of mixtures, okay? If it is uniform throughout, then what we call it, we say that mixture is homogeneous. Okay, the example here is tea. Whether it's unsweet tea, whether it is sweet tea. My favorite example, if you watched my video, my intro video, I said I like ice cream a lot. My favorite example of a homogeneous mixture is pure vanilla ice cream. When you take a bite of good pure vanilla ice cream, every bite tastes the same. If you're drinking this glass of tea here, every sip is going to taste the same because it is uniform throughout. It's a mixture that's uniform. So if you're looking at, I know this picture looks crazy. There's a lot of things going on. These big molecules like this might be a sugar molecule. And then you'll notice these smaller molecules might be water. All right. But the sugar is dispersed throughout. Okay. It does not look like the picture neighboring it, which is not uniform. Okay. This one is not uniform. It's not a uniform mixture. This one is uniform. It's a uniform mixture. Okay, meaning there's multiple things involved, but everything is spread evenly out. Remember the vanilla ice cream example. What is in vanilla ice cream, by the way? You've got milk, you've got ice, which is water. You've got air particles whipped into the ice cream. You've got sugar particles mixed into the ice cream. You've got fat particles, okay, or molecules, I should say. And all that should be in good ice cream, evenly spread throughout the mixture, all right? So that we call that homogeneous, all right? You need to know these terms. Last term, heterogeneous, if the mixture is not uniform throughout. Example, sand at a beach. If you scoop up a handful of sand, you might get a whole bunch of wet sand down here and you might get a whole bunch of water on top. All right, that is not uniform throughout. You got a whole bunch of water come together, you got a whole bunch of sand come together. So that is called a heterogeneous. Another example would be a plate of spaghetti, a bowl of vegetable soup, different things like that. If you threw in a bunch of Oreos into your vanilla ice cream, now you have a heterogeneous mixture because not every bite's going to be the same. You might get a big piece of Oreo in one, you might get a small piece of Oreo in the other. You might get all ice cream in one bite. Does that make sense? So that is the difference between heterogeneous and homogeneous. Questions on this slide? Because here's where things can start to get confusing. It's a lot of words, a lot of definitions. Any questions? All right. So we're about to wrap up. We're almost at 12:05. The main things that you should have taken away from today. Number 1, the difference between, I'm going to abbreviate, chemical and physical changes. I wrote that awkwardly, but I'm going to write it underneath. Okay. Number 2, how to classify matter. Okay, so we defined what matter is. We looked at how to classify it. And then also I'm going to put a little star in here. We looked at the 4 signs of chemical changes. So 2 big umbrella things and then some smaller things underneath those. So lastly, we're going to get to this with chapter 3. These are called polyatomic ions. And in just our last few minutes here, I want you to go ahead and start working on memorizing 11. We're not going to memorize everything on this chart. There's a lot, but there's 11 very common ones that as a nurse, as a dietetics person, as a health professional, you should recognize what some of these polyatomic ions are. So I'm going to box the ones that you need to know in. Okay, that's going to be the hydronium. I think these first 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Yeah, these first 5. You need to know these. And when I say know them, I want you to know the name and I want you to know the formula. And you'll notice the formula has a little charge associated, positive or negative. And sometimes it's a -2, okay, or a -3. And this one down here, the hydrogen carbonate ion, that's a long word. Just know it by the parentheses, bicarb. I'm going to say that, especially when we get to acids and bases a whole lot, bicarb. So you can call it bicarb. And we say bicarb, that's HCO3 minus. Okay. Any other ones? Okay, hydroxide is an important one. Very, very important one. Very important part of our blood buffer system, which we will get to way later. Nitrate, nitrite. Okay, yes, these 2. What are we at? So far, I think there's 11. 1, 2, 3, 4, 5, 6, 7, 8. And then phosphate is 9. And sulfate and sulfide. Okay. These are the 11. I want you to have their name memorized and their formula memorized. Okay. So these won't show up on quiz number 1. We're going to have a quiz next week sometime. But starting with quiz number 2, I'm saying they're fair game. Okay. Meaning I could ask you to identify the formula. I could give you a formula and ask you to write the name of it or identify the name of it, so on and so forth. So that's it for today. Thank you guys for joining. Glad we all made it to the Zoom. And I will see you, if you have lab on Monday, remember show up with your goggles and watch the video about how the flow of our building works. If you have lab on Thursday, or if you have lab with Dr. Baldwin, you'll show up on Wednesday, and you do need to have your goggles. Shoot me any questions via email. If you had questions from the lecture and you just didn't want to ask it out loud, that's perfectly okay. Other than that, you'll have a great weekend, and I will see you 10:50 on Tuesday or lab on Monday. All right.
What's the one at the bottom? Sorry, I can't see it.
Good sulfite.
Oh, okay. Thank you so much.
You're very welcome.
So if we don't have lab on Monday, do we
Yes.
still have like the other like a dry lab or whatever it is?
Yes, if you don't come in for the wet lab, on the lab schedule for the syllabus. In fact, let me hop over to our syllabus really quick. Here's our syllabus and here's our lab schedule. So I have a bunch of things highlighted, but if we're looking at next week, so if you're in group A, and remember there's a PDF on Blackboard, if your name's not on it, let me know. But if you're in group A, you're going to show up and we're going to go over safety and detecting signs of a chemical change. This PDF is in Blackboard in the labs folder, online classroom tab. If you're in group B, you will stay at home. You will download and print out the conversion specific heat density dry lab. Now, we're really going to get into some of this stuff next week. So I wouldn't sit around all day Monday trying to do this dry lab, because we're really not going to lecture on it until Tuesday and Thursday. It's not going to be due on Monday. I haven't even stated when it's due yet. But if you're doing the dry lab, if you're in group B, you're probably going to have all week to do it, okay? Because we actually have not lectured on how to work density problems, how to work specific heat problems, or how to do conversions. So I will tell you when that is due It is not due on Monday. For you Group A people, you'll come in, complete the lab, and I have not even said when that wet lab is due yet. It'll be due online. You'll just come in to get your data. And then you will have time, okay, probably a couple days, to put that data in online and complete your assignment online, okay? Okay, great question. Thank you for clarifying that. Only the Group A people are going to meet in lab this next week, and then the Group B will come in for their wet lab following, and the Group A people will do the dry lab. Any other questions? Thank you.
If we're meeting in person, do we just need to print off this stuff and bring it with us?
Yes, that's
Okay.
what I would do. Or if you have a tablet, sometimes people just bring their laptop. That's fine too. But you're not going to have a ton of countertop space, so I would just print it off and bring it in, and you can copy it all down, and then you can put it online later. Any other questions? These are great questions. Okay, well, I will stick around if anybody has a question, but we're past time even, 12:06, so y'all go enjoy your day.
For the reading, oh, is she, oh yeah. For the reading assignments, quick question. I see, so I did the 1 through 5, and then for next, like the 25th for our lab, we have the next, like just keep going with the reading.
Yep. So if you look at our syllabus schedule, here's the reading that I assign for each lecture.
Mhm.
If you have the text, if you don't have it yet, don't worry, you can catch up over the weekend or when you get it. So what we talked about today should have matched what you read in sections 1.1 through 1.5. And what
Yeah.
we're going to talk about next Tuesday will match and correspond to 1.6, 1.7, and 1.8. Notice I don't have 1.8 and 1.9 on there. So don't read those sections. Okay.
Okay. And
Yep.
then with the like when are our mastering chemistry assignments due?
So once you get access, you'll notice, and I'm gonna emphasize this real quick. Let me scroll up. Here, homework. Right here. Homework assignment. So let me turn this sideways so it's bigger. You will see when you get access to Mastering Chemistry when the due date is. Okay, and pay attention to it. It says assignments are to be completed by the date listed on the syllabus, meaning they're due at 11:59 p.m. the day before. I want them completed by that day. And that's kind of confusing. I get that.
Okay.
Some people think I have midnight until that exact day. No, I want it completed by that day, by the arrival of that day. So it'll be due at 11:59 the day before. And Mastering Chemistry will tell you the exact date and time. Okay?
Okay.
So for example, homework 1 must be completed by September 1st. So in Mastering Chemistry, it'll be due by 11:59 p.m. on August 31st.
Okay.
I think the first assignments we have due, we go down to the schedule. I don't think I know. It's an intro to Mastering Chemistry. It's just kind of an introductory thing. These both are worth 5, and what we call a chemistry primer, they're both worth 5 points. I can't remember which one, but I think the chemistry primer, I'm not penalizing you guys for any wrong answers. So you get as many wrong answers as you want. And if you do it, you'll get the 5 points. Okay. Thanks for asking that because I forgot to say that.
So quizzes and homework, are those both on the Mastering Chemistry, or are those going to be on Blackboard?
Homework is all Mastering Chemistry.
Okay. Perfect.
Quizzes, there may be times I use Mastering Chemistry to write a quiz. It's easier for me to write in Blackboard though, from my
Okay.
experience, and I only have experience from the spring when we all shifted online. So right now my plan is to use Blackboard for quizzes.
Okay.
And I will definitely give you guys a heads up. Hey, you have a quiz. Here's when it's due, blah, blah, blah. And here's how you access it. But I'm planning to use Blackboard for quizzes. Mastering
Okay.
Chemistry is where all the homework assignments will be.
Okay. Thank you so much.
Yes. Any other questions? These are all great questions.
When you said before you sent out those emails, I didn't get any of those emails, but probably because I got in the class late. I didn't get in the class until yesterday.
Okay. Welcome. Okay. Welcome to class. If you are new, meaning you just got added Monday, Tuesday, or Wednesday of this week, my email is right up here. And I'm going to give you a second. You can write it down. Right here. Here's my email. Shoot me an email and introduce yourself, and I can catch you up to speed on everything you need to know. Okay.
Okay.
So I'll make sure you have all the info you need to know. I'll share the videos that I've shared with everybody else that walk you through our Blackboard course and whatnot. So shoot me an email, and I'll make sure you have any information I've sent to the rest of the class.
Okay.
Yeah.
And then my other quick question was, I went to the bookstore website to rent the book, and above that it was something that was like $86 that said it was required. I don't know if it's the mastering access code, because you just said that it wasn't available.
Well, I've been getting lots of emails from students, and it may be available starting today. So far, a lot of students have emailed me and said the access code's not available. The access code's not available. They may be available starting today. I just sent an email, I think yesterday or so, saying it's okay if you didn't have it right now, but you do need an access code. And I think all that, I keep wanting to scroll on my computer.
They emailed me my access code yesterday, if that's helpful.
Thank you, Abby.
Mm-hmm.
Oh, so they should be getting them in. Right here on the syllabus where I talk about homework, here's how I talk about how you can get access. Okay, there's a PDF on Blackboard in the online classroom tab that tells you how step by step to enroll in our Mastering Chemistry course. And you do need an access code, so I bet that's what that $86 was.
Okay, because it says the title of it is fun period of general ... mod mastering.
Yes, fundamentals of general chemistry.
Okay, I just want to make sure that it's the right thing before I buy it.
Absolutely, I don't blame you. Okay, so yeah, you want to make sure it's an access code. If you don't want to play around with that, you can just follow the steps on the PDF on Blackboard, and then at one point you'll be prompted to give an access code. And if you don't have an access code, there's a site or a spot where you can click on get temporary 14-day access. Click on that. It'll give you temporary access for free starting out, and then it will prompt you at any point you can pay, and it'll give you permanent access. Okay.
Okay.
So. Okay.
I think that's all my questions.
Good deal. Any other questions? Okay, well, I'm gonna hop off. We'll see y'all later. Email me if you have a question.